Hello, in this video I'm going to give a brief outline of some of the problems with the standard model of particle physics. We've discussed in previous videos the successes of the standard model and some of its content and some of the predictions that have been made, such as around neutrinos and Higgs boson and things like that, and how those have been substantiated with evidence. But that doesn't mean that everything with the standard model is all hunky-dory. There are still some issues. So I'm just going to mention a couple of them here. So let's start then with gravity. So there's a real problem there that we've got quantum descriptions of the electroweak force, so that's covering electromagnetic interaction and the weak interaction, and also for the strong nuclear interaction. So those are all included in the standard model and descriptions using quantum field theory, as in we can describe using fields how these interactions are working at the subatomic level. But there is no such theory that works for gravity. We don't have a description for gravity inside the standard model and associated theories. So at the moment, gravity has still got its best description that we have is general relativity. And no one has been able to make general relativity compatible with the standard model and quantum mechanics. So that's probably the most famous problem with the standard model at the moment. And that's why you hear things, if you're a fan of the Big Bang Theory and other such things, you'll hear terms like, loop quantum gravity thrown around and such like. And these are the sort of theories that are getting proposed and investigated and thrown around in the science world to try and make gravity compatible with quantum mechanics. So, and this causes a lot of problems. I mean, it's nice for completeness sake. This is one of the things that we were saying about physics all in all. One of our aims is we just want to get the best descriptions possible of everything. There's value just in knowing this sort of thing, but it just throws our predictions and understanding of so many other things. When up to a point, there can be there isn't always a problem with this because gravity is so much weaker than the other forces that quite often when we're considering the effects of gravity, the other fundamental forces might not be as much at play. But if you're looking at the early universe, where you've got very dense conditions with a lot of gravity thrown around, and you've got the electromagnetism and all of the fundamental forces coming together, then this is one of the reasons why there is no particularly good description of the early universe. So that's one of the big problems. How are we going to get gravity incorporated into it so it's all compatible? Another one, talking about the universe, is stuff to do with dark matter and more recently dark energy. So because it wasn't that long ago that everyone was just talking about dark matter when it came to the fate of the universe. So we know that the universe is expanding. That's something that I'll discuss later on when we get onto videos about cosmology and such like. But you've got the universe, it started with a big bang, it's expanding, and there was always that question of, well, is the expansion slowing down, or what? Is it going to slow and then just slow to a stop, or is it going to slow and then contract again? Well, observations have shown that actually the expansion seems to be accelerating. So the original calculations were all based on, well, it depends on how much stuff you've got. If you've got enough stuff, the gravity will slow it and then it will crunch back again. And that was looking at dark matter, but no one knew what this dark matter was. They say, well, there's everything that we're looking at, all of the observations that we're making and the matter we can see in the universe doesn't seem to add up to the observations, particularly when they were looking at things like how galaxies were behaving. galaxies were rotating in a way that should just blow them apart unless they had more mass. So there's a lot of stuff that is in the universe, like actual matter, that we're apparently not observing. We don't really know what it is. So there's a big question there as to whether there are other fundamental particles that we don't know about. But then more recently, over the last 20 or 30 years or whatever, there's been this discovery of dark energy. I mean, it appears that the acceleration of the universe is speeding up. And there's some kind of energy which is driving this. But again, we don't have an explanation for what this energy is. Where has it come from? How is it operating? I mean, it's just that we've got two big unknowns here. Have we got some kind of new field, some kind of new interaction going on here, which is driving this and containing the dark energy? Because it doesn't seem to be explained by the ones that we've currently got in the standard model. And similarly for the dark matter, are there other particles around? So a couple of another two big unknowns there. The third one that I'm going to mention is the asymmetry of matter and antimatter. So you would have heard me mentioning symmetry quite a lot all the way through this. So much of the standard model is based around these ideas of symmetry, and we've got all of these fundamental particles, and we know that we've got the particles and the associated antiparticles. So we've got matter and antimatter. But why is it that everywhere we look around the universe, we're seeing loads of matter and we're not seeing the same amount of antimatter? Why is there lots of one and not the other? Why is there this asymmetry? I mean, is the antimatter somewhere else? And where did it go in the Big Bang? If it was created in the Big Bang, well, where is it now? I mean, it hasn't annihilated with the associated matter. They haven't combined and just released some energy. So where is it all? Did it go into some other universe or something at the Big Bang? Or were there different rules back then? Were there different rules around, in the very, very early universe and around the Big Bang that meant that more matter than antimatter could be created? I mean, who knows? But again, it's another one of those things that doesn't seem to be explained by the current theories, that we've got this asymmetry. Now, we've seen cases in some of the descriptions that we've already been through where these asymmetries can suddenly appear. This is one of the things that we were talking about with the Higgs boson, wasn't it? So maybe there's some other process that comes in that allows some kind of asymmetry to happen. So we've got 3 or 4 really big questions here about how to get gravity into the standard model, how to explain dark matter and dark energy, and how to explain this asymmetry of the amount of matter to antimatter in the universe. So these are all huge challenges, and these are things that people have been working on for a long time. I mean, decades and decades on a lot of them, and not really getting very far at the moment. So who knows how long it will take to figure all this out, but the joy of science and all of that.